Welcome to Unapologetically Technical. My name is Jesse Anderson, and this is the show that's different. We go deep, we go all the way down. We are unapologetically technical about it. My guest today is Jeff Chow. He is the co founder and CEO at Sync Computing. Welcome to the show, Jeff. Would you mind telling us a little bit more about yourself?
Hi, Jesse. Great to be here. My name is Jeff. I'm the co-founder and CEO at Sync Computing. My background, I got my PhD from UC Berkeley in electrical engineering and computer science. Then I went to MIT for a postdoc. I got my PhD from UC Berkeley and in electrical engineering and computer science. And then I went to MIT for a postdoc. And then I went to MIT Lincoln Lab, where I was a staff research scientist. And then from there was kind of the inspiration for Sync Computing, our startup. And that's when we kind of transitioned from academic research to startup land. But that's my background.
Yes, so I'm excited about this. I always love to talk about the transitions between states. In this case, the transition between academia to startup. So I'm really curious to hear about that. You didn't talk about it specifically, but some of those research roles that you had were about simulations. Why are simulations so important?
I've been doing simulations in some form or the other for a long time. So in grad school, I was doing a lot of optics and device research. And in that world, you have to simulate because it's very expensive to do experiments. And so it's much faster and quicker if you can kind of get a rough idea with simulations to kind of hopefully get an idea like, okay, this experiment is worth it or that experiment is worth it. And so simulations just allow you to kind of explore a broad space very quickly and cheaply. And so that's kind of how I used it a lot.
Are we living in a simulation?
We could be. You got to always check the back of your neck if you have that matrix plug. So we'll see. If this is all a simulation, I'm curious what kind of compute engine we're running on because it's very smooth. So I'm very impressed.
Yeah, yeah. There's a lot less lag than there
Yeah,
should
I
be.
don't see much lag, so it must be a very powerful computing machine.
The other one that I've read is people will flip a coin and they say that's how they know that they're either dreaming or in a simulation, and that's kind of funny too. Okay,
Right.
which way will it fall? How will you know the
Yeah.
right way it falls? Okay,
Right.
you talked about the optics and how expensive it was to do optics. Why is optical so difficult then?
You mean from an experiment standpoint?
Yes,
Why is it?
from an,
So when you're doing kind of optics, it's very expensive. You have to buy a bunch of stuff. You have to buy a laser. You have to buy mirrors. You need an optical table. You have to. It's like thousands and tens of hundreds of thousands of dollars of all of the equipment that you have. And then if you're fabricating actual chips and devices, that's hundreds of thousands of dollars, even more. So, and you really only have one shot because you're in grad school. You're not there forever. So, you only have a few shots at actually building something that works in the way you hope. So you try to simulate and prep as much as you can before you like pull the trigger and actually build something. Because if you're not simulating, you're not trying to model, you're not trying to understand, you're who knows what you're building, like what it might not work.
that is an interesting approach. I've always found it interesting. I've spent my entire career in software. I've never had to cross over into that physical realm, and probably to our detriment because I'm curious how you, as we talk later on, you're probably going to be taking that background in simulation and applying it to sync computing as well. So one of your first
Yeah,
company, go ahead.
sorry, go ahead. I was just saying I've kind of transitioned not just from academia to startup, but also like from the physical to the software. So I've definitely also had that kind of interesting journey as well.
It is an interesting journey, and we'll talk about that more. But your first position, at least the first position you list on your LinkedIn, is at Anoka Microsystems. Did you found that company right out of school?
Yeah, that was actually with my professor at the time. We did it towards the end of my grad school tenure, and it was only about a year. And it was in partnership with HP, and they actually gave us our first kind of customer check. to kind of build this device. Um, and so that was my first taste of a startup life to kind of see what it was like. It was just me and my advisor, just trying to build a thing for HP essentially. And so it was an interesting journey. It was an interesting 12 months. We got the funding and then we had to build the thing. But then HP's kind of direction changed and we weren't really sure where things were going to go. Um, and my personal life was also changing. So I thought, actually, I would like to try something new. So that only lasted about 12 months, but that kind of gave me my first taste of startup life.
Did that make you want to try startups again, or did it put a bad taste in your mouth?
No, I think it kind of maybe broke down the barrier for me. I kind of saw what it was like. It was actually very similar to grad school because grad school is very raw. You don't have much. It's just you by yourself doing stuff. So startup life and grad school life, I think, are very similar in the sense that you're not part of this giant juggernaut corporation with like layers and layers of bureaucracy. It's really just you and your idea, and can you build it and does it work? So I think those who've done like grad school research stuff would find that a startup's actually a similar mentality versus coming from like a giant company. Actually, going from a giant company to startup life, I think, is a bigger jump than like research, in my opinion.
You also mentioned that there was a change in your personal life. I think that there's a Goldilocks zone of there's this zone where you're young in life and have less to lose and less that
Yep.
you're feeling like you're missing out on. And then there's a later in life sort of thing that you've you've now been at that company, a big company, and you're saying, I want something new. Is that kind of your experience as well?
Yeah, I could definitely see that. I've had a couple different jobs and I've worked for like big corporations. The biggest one is like the government. I worked in like government research and you can kind of see the bureaucracy is real. And so some people like it. Some people kind of get frustrated. You just feel like you're handcuffed and things move slow and you're just waiting. I'm probably more in that bucket, which is why the startup life was always kind of appealing to me. It just seemed like, oh, I can actually like do stuff. I don't need to wait for 10 approvals. Like I can just build and then see what happens. So that was kind of nice.
It is. It is. I see it every so often, and I see LinkedIn posts about it. Uh, People saying, "Why don't I work at big company X?" It's not like you couldn't. They couldn't work there. They couldn't make it or
Mm,
something. There's often that feeling where people say, "Oh, you couldn't work at Fang, for example." Well, I choose not to work at Fang. There's a reason why.
right.
I have friends that work there, and I know the stories. So yeah, it's a
Yeah.
very big trade off there. So from there, you went to UC Berkeley as a graduate researcher. Uh, what made you want to go back into academia from there?
Actually, I think the timeline is a little jumbled if you're just going on LinkedIn. But so Anoka was part of my grad school, so um, experience. So I was always in academia when I did Anoka, and then from there I went to postdoc at MIT. So maybe you're wondering why did I go from Anoka to a postdoc?
Yes.
I think I was still very interested in research and kind of advanced ideas. Also, MIT is a cool place, and I wanted to kind of see what MIT was like and kind of work with some you know top notch folks over there. So my passion's always been building new things, researching new things. So that's kind of what kind of drew me back.
And was it everything that you hoped it would be?
It was kind of what I expected. It was I had some observations, perhaps the differences between UC Berkeley, a public institution, versus MIT, which is private. Um, I think the amount of funding and money that MIT has is tremendous, and I even taught, or at least helped out in teaching some courses at MIT when I was there, and the classroom sizes were much smaller at Berkeley. It was kind of like you're a grain of sand on a beach. And then at MIT, the classrooms the sizes were so small. And I TA'd in both schools. And at Berkeley, I was like one TA for like 50 students trying to figure out how to do something. And then at MIT, I was like there are four TAs for 12 students. So just like the ratios were way different, which was kind of interesting. That was kind of new for me. But the research experience was pretty much identical. That was kind of what I expected.
Hmm. Did you notice a significant uptick in learning as a direct result of having that low of ratio?
I think so. That was like my teaching experience at MIT. So I did both teaching and research. So from a teaching perspective, I think it's much better for the students to have a much smaller ratio, right? You get more one-on-one time. I remember feeling when I was an undergrad and grad at Berkeley, like you don't get a lot of exposure or one-on-one time with the TA or the professor. It's just kind of up to you to figure things out. Um, so I think it's, tales all this the time, good student to teacher ratios, I think are always beneficial for the student.
A related, more Gen AI question is I think one of the manifestations of Gen AI is a very personalized teaching where, even at scale, you could be personally taught computer science, whatever you were teaching. Do you think that that's the case, or do you think it has to be a human on the other side of that still?
That's a very interesting question. I haven't personally used Gen AI to. I've seen some videos of it, and it looks pretty cool. I mean, there's such a wide spectrum of teaching, or teaching like kindergarten, elementary school, high school. What's the caliber of student? Is it like the advanced students or the ones that kind of need help? My teaching experience was more like in grad school. Those are really good schools, and so everyone was kind of like a top performer. I think at that scale, Gen AI will be hard. One, because we're teaching very advanced concepts, and so it's not like there's a bunch of like material you can base your training off of. Like these are like really advanced concepts. And then two, you really have to understand what the student is thinking and what questions they're asking and in their background, because usually the one way to teach kind of advanced concepts is you have analogies. You're like, okay, this thing is like this and this thing is like that, to kind of root it into something they do have a good understanding of. Can Gen AI make up analogies? I don't know. If there was already one posted and then Gen AI used that and regurgitated it, sure. But can Gen AI create an analogy? I don't know. I have never actually tried. That might be a really good test. Um, but I think it might help some subset of teaching, but I am skeptical it would just replace teachers.
There was an interesting demo that Google did at Google I/O of them teaching physics with basketball, but that was part of the prompt. He said, "My son loves basketball. Teach me physics with uh, with basketball."
That's cool.
And so that would be probably similar to yours. Of you would have to say, "I understand," or "I'm coming from this background. Teach me it this way." And in some ways, I don't know if you learn this way, but a lot of times what I'm doing is I'm trying to take whatever concept and figure out what's the most similar from my background to it to figure that out. So it'll be interesting to see if Gen AI can do that or how much coaxing we have to do.
hmm Probably for one
Yeah.
of the more basic, like middle school, high school materials, it's Gen AI has a higher chance of succeeding there because there is so much material out there to train on, and the concepts are much more kind of straightforward. But like when you're teaching quantum mechanics, and it's like, what's the analogy of this relative to your life? It's a bit more nuanced, I think.
So that's what you're teaching. You're teaching quantum mechanics there.
I taught some device physics, which does use some quantum. Um, so yeah, that was back in Berkeley when I was teaching kind of upper division classes.
Nice. And so, on your LinkedIn, you talked about you were writing simulations there too as part of your postdoc. What sort of simulations were you writing?
Yeah, I was doing more kind of optical and device simulations in the sense of this was the interaction between light and matter. So when light hits something, what happens? And this was at that time I was doing kind of solar energy research. So how do you convert a photon into useful electricity? And so step one of that is the absorption of the photon. So how do you create a thing that absorbs the photon versus being a mirror that just reflects light? How do you actually capture the light and do something with it? So there are a million kind of not a million, I'd say 5 or 10 really good optical simulation tools out there. So I was doing kind of a lot of that kind of work.
So how do those tools work? They're basically here's a physics engine that understands photons, and then you're programming some changes to that.
Yeah, there are many flavors of this. So the one I was using was like finite element simulations, but basically it's all based on something called Maxwell's equations, which kind of tell you how electromagnetic waves propagate. So light is really just an electromagnetic wave, and you use finite element or FDTD to kind of simulate the propagation of light in any medium. So, for example, if you have sunlight coming in, it's propagating through air. So you have what's called boundary conditions. So one boundary is like you have the sun that's just emitting light, and then that is just propagating through space. And then you have some sort of surface or material that the light is hitting, like a solar cell. And so you have a bunch of information like the structure, the shape of the solar cell. Is it flat? Does it have a grating? You have the index of refraction. You have the material breakdown. And so you can kind of understand and see, how does that light from the sun actually, what is the conversion efficiency from free space light into actual captured light? So you're basically setting up the physics and the boundary conditions, and like, all right, there's a light source here, I have material here, and then you click go, and then the simulation will just simulate light propagating, hitting the thing, and then the output is like, okay, this was the absorption, it was 30% efficient, 50% efficient, etc.
I
Hopefully that made sense.
it did make sense. So you could actually simulate out and say if I change this slightly, then what is that absorption? I see.
Yeah, that's the
What
whole thing. So you simulate, you try different geometries, then you go, okay, this one looks the best. And then you go, now I will switch from simulation to experiments. And now let me go build that thing. And like, let's see if reality matches simulation.
where do you come since you've dealt with solar panels so much? Where do you come down on this? Of will we ever be able to have a true solar future, or will we need some other power source as well?
That's a good question. I think we're getting obviously lots of money going into this space. It's getting more and more efficient. I think there is, of course, a limit into how efficient it can be. Um, and so now we're reaching like fundamental physics of like, well, we just fundamentally it's hard to do significantly better. So that's why I don't think we're gonna see like huge jumps in efficiency. It'll be like, you know, fractions of a percentage in terms of the efficiency improvement. But probably from a business standpoint, the economics are interesting. I think just serving from my memory, but maybe 10 or 20 years ago, like China just massively subsidized all of their solar cells. And I think they wiped out a bunch of US companies because the Chinese solar cells were so cheap because they were government subsidized. And so, there's the science part and then there's the economics business part. Um, so it's a very complex landscape. So it's not just can we make it more and more efficient? It's like, well, is the government going to subsidize these? And then, um, and then two, the end customer, are they going to put them on your roof? You can drive around now. A lot of houses don't have any solar cells on their roofs. Why? Why don't people do it? Is the ROI not there? Is it kind of painful? Um, so it's a very complex industry, and is it going to be a sustainable market? Is it going to grow? Is like any other product. It kind of depends on a lot of factors.
Well, I listened to the Elon Musk biography, and they have this whole section talking about the solar city, and they talk about that kind of over time. And one thing that I never thought about was just the install difficulty, the sheer difficulty of installing something consistently on a roof where there's no consistency to the roof. There's no, it's always going to be this slope or it's always going to be that. It's just here's here go put it on there and see what happens. But what was another part that was interesting was that the engineers had never actually done an install. So they were very, very separate from the problem. And it kind of reminded me of where we're at in both data and I would say still in software of that separation between the person trying to do and the person trying to actually the product that's being created. And that the further that separation is, the less value we're creating.
That's very true. Yeah. It's one thing, it's kind of like academia. Academia, you're very, very far away from actual use cases. You're just trying to prove a fundamental concept, but will that actually translate to a useful product? No clue. But I could probably publish like a Nature paper, but will anyone ever use it? Odds are very, very low. Most research turns in nice papers and then they stop because actually making it a product is, I would say, several orders of magnitude harder than the first kind of initial research.
Well said. So speaking of more research, you went to the MIT Lincoln Laboratory and you were a member of the technical staff. And there you talked about creating an analog distributed system. And I have never seen those three words together before. I'm really curious about what an analog distributed system is.
Yeah, this was a really fun research. It was purely like a passion curiosity project when we were there. The basic idea is, modern computing, which obviously is fantastic, is all based on digital bits, right? Zeros and ones. And for good reason. It makes a lot of sense. And the transistor, and I don't, everyone knows the success of all of that. There has always been a secondary line of thought, even back in the 60s and 70s, that you could compute on something called an analog signal, meaning instead of zeros and ones, now you let the voltage be whatever, any continuous value, 0 volts, zero point 0.1 volt. Because right now, today in the binary world, like 0 volts is zero, and then like 5 volts is one, right? And then anything in between basically gets rounded to one of those two. So there is a domain in which, well, what if we don't round, and what if we actually have a lot more information in the bit? Because right now the bit has one value, one piece of information. Are you a zero or are you one? But what if that one bit now could be an infinite number of values, like 0.23 or 0.778, right? And how much more could you compute if you were in this analog domain? Um, so that's kind of analog computing, which is not a new concept. It was born at the same time as digital computing, but digital took off because it was much more scalable. But analog computing, some of the benefits were that you could do some computations much faster. For example, a lot of differential equations you can compute very quickly in nature. Um, One really good example is like, when it rains and then rain collects in puddles, right? How did the water know to collect in these like dips in the concrete? Did we have to run a computer to simulate it and tell water droplets go here? This is the minimum. It's like, no, you don't have to do anything. Like nature, gravity, the curvature of the pavement naturally collects the water. So, you could think about it as like, well, if I wanted to compute, give me a slab of concrete and I want to find the lowest point in this concrete, I could scan it and run a huge computational simulation on it. Or I could take a bucket of water and just throw it on there and then just see where does the water accumulate. And then that's probably the lowest point. Um, so, that's it's kind of a high level cartoony example, but that's an example of like why nature and analog could be very powerful because, what you're trying to answer a certain question. And it turns out nature can actually help you answer those questions very quickly. And you don't have to go into an Excel spreadsheet or write up a Python script to kind of simulate everything. You can just use nature. Um, Sorry, this is a very roundabout explanation, but I'm kind of giving you like the high level background of analog computing. So the research that I did at Lincoln Lab was kind of using these things to solve optimization problems. And so there's an optimization problem called the icing model, which actually kind of bleeds into the quantum computing world. Um, but it turns out you can potentially solve these kind of optimization problems very, very quickly with analog computers, much, much faster than using your laptop or a supercomputer. And that was kind of the fundamental motivation.
And how is it distributed then?
Um, Distributed, I guess I'm not, it's a little blurry to me what distributed means.
Uh,
So, um, yeah, I'm not sure. It's distributed in the sense that it's a bunch of parts working together. Um, so if that's the definition, then that's true. Basically, the we built this analog circuit that was a bunch of components all kind of coupled together, and they, as a group, worked together to kind of optimize and solve this math problem. So maybe that's the definition of distributed there, but it gets a little blurry. Depends on what your definition is.
okay. Yeah, that is blurry, but it's interesting you bring up that point. It wasn't until I started talking to some of my friends about quantum computing that I realized how much it once you hit a very specific problem that quantum computing, or in this case analog, could do, how wildly different it was. And it was a lot of what when I talk to people about what you would throw at quantum computing, it was these optimization problems where they could do it in a blink of an eye, where with digital systems, computer systems, it would take forever.
Right, right. Yeah, that's kind of always been the pitch and the promise of quantum. Personally, I sit probably more on the skeptical side of quantum computing. I've been in the weeds and I've kind of seen um, what has to happen there. So in theory, it's great, but again, this is perhaps the divide of academia and reality. So academically, yes, theoretically, it could be very powerful. Practically, building a scalable, fault tolerant quantum computer is massively, massively difficult. Um, Actually, quantum computers, in some sense, are in the same flavor as an analog computer, because they don't use just zeros and ones, right? They have these quantum states. Um, but it's the reality is it's really hard to make that real and to make it solve a real problem. Like today, there's no your phone, your iPhone. It could be 10-year-old iPhone is can solve more useful problems than kind of the most expensive quantum computers today. So there's a long way to go. I'm a fan of research, and I think they should keep on going. But it's really hard.
Okay. Well, I guess speaking of more research, from there you went to Activate and you were an entrepreneurial research fellow. What research were you doing there?
Yeah, so that was part of the origins of sync computing. So we basically we published this paper in Nature Scientific Reports, and that got us kind of our first funding to kind of spin out a company to try to commercialize this kind of analog circuit, this kind of original idea. Um, and Activate at that time was kind of a program that helped PhDs try to transition very academic, hard tech ideas into commercial realities. And so we got accepted into that program. But it was this analog computing thing that we were trying to commercialize. And so Activate basically, it's a fellowship. They give you some funding, they give you a stipend. And so they really helped us try to figure out how do you actually commercialize something, which is commercializing fundamental research is really, really hard.
You've said that. Would you mind? Because I think people, I've never talked to anybody about this, but tell me more about why it's so hard.
Um, I mean, yeah, I'm speaking generally, but I'll try to be specific in my case, of course. We could solve this optimization problem very quickly. And from an academic standpoint, great, green check marks. You have done what the academics say is what should be done. Then you go to the real world and you start asking people like, so do you like this? This math problem that I can solve really fast? Do you care? Um, and particularly in the optimization space, there are so many challenges in the real world. So, for example, we spoke to UPS for a bit. So UPS obviously ships packages all around the world, and um, they have what's known I don't know if you've heard of the famous optimization problem, the traveling salesman problem, which is like, okay, you have, thousands of cities and a million trucks, and optimizing the routing will help save a lot of time and gas and money, right? Um, and they have some of the world's best kind of the field that does this kind of research is called operations research, OR. So they have some of like the world's top minds there, and they're excellent. And so when I spoke to them, they were like, "Well, it took about a year to come up with the algorithm, but then it took about 9 years to convince the company and to install all the sensors and to do training for all the drivers. Because one of the things about optimization is like you need perfect information. Like if you're off, or what if a driver wakes up late or makes the wrong turn? Your very tight, highly efficient algorithm now just is completely destroyed because someone made a wrong turn, right? So there's a huge gap between like, okay, academically, yes, I solved this math problem, good to go. UPS, go save, a bunch of money. And then the reality is like, well, actually, the world's not so clean. It's not so perfect, especially when you have humans. That was kind of one big lesson we learned. Like anything with humans, oof, good luck trying to optimize. Humans are so unreliable. And I speak for myself. I don't wake up at the same time every day. I make mistakes, right? Like it's just humans are error prone. And so to have humans so tightly coupled to like a mathematical algorithm, it's really hard. Which is why we kind of pivoted towards computing because, okay, let's just focus on computing and the internals and electrons moving and stuff like that, memory. It's just much more deterministic. We don't have to rely on some person waking up on time and following instructions. Um, or we don't have to, someone gets sick, that'll mess you up too. Um, so I don't know if that answers your question, but that's, when you're in academia, you're building in a vacuum in like the most clean thing where everything is perfect. You have perfect information. Everything is flawless. Everyone does what you say. The real world is so much messier. And I think when you cross over to the real world, math kind of falls down. And because math is very rigid and very precise, and the real world is just the complete opposite.
It's kind of like those jokes. The engineer walks into a room with a mathematician, those sorts of things, where the mathematician says, "I've solved it," and the
That's
physicist
right.
says, "No, you haven't."
That's right. That's right.
And the
Yeah,
engineer says,
mathematically, it's
I've
beautiful, but
approximated it, so that worked. It worked well enough, and it took me less time."
that's right. That's right. There's probably a lot of this in the software engineering world too, right? Like, let's just ship something out quick. It roughly works. That's good enough. Bunch of heuristics. Like, yeah, okay, this should be generally right. Like, you don't have to spend 6 months researching like the absolute best way to do something, best architecture. It's just like, well, it's better just to ship something fast and get feedback and then iterate versus like perfection. And perfection is probably a myth in the real world.
It is. Yeah, you bring up some good points that are there of that desire, that search for perspection. I would say even in data, even though we were talking about research or humans are messy. They're just there. They're going to muck everything up. Life happens. And so
Yeah.
if you're there designing something for steady state, for the happy path, that doesn't happen. And I see that even in software, your unit tests. Happy path, happy path,
Yep.
happy path. Okay, and now show me your negative tests. Don't have those. Okay, well, that's a
Yes.
problem. Let's see
Yeah.
what happens
We
when you
encounter
send it
this a
all
lot.
in.
Yeah. We encounter this a lot. Like, testing is hard because everyone just kind of builds happy path stuff. And then you think no one in the world would ever not do my happy path, right? And then of course the first customer uses it, immediately breaks your your logic, and you're like, wow, okay. It's hard, right? You don't know what another person will do with your stuff. They're not you. They think differently. They see the product differently. Um, so yeah, the real world is messy. Humans are messy. It's just really hard.
Were there any other learnings you had?
Like in the early days, transitioning from research.
Any sort of learning as you made this, as you were trying to, as you were there at Activate, trying to take that theoretical product, or let me back up. One of the issues I saw probably 5 years ago, maybe earlier than that, doesn't happen as much now, is people would hire somebody in their PhD and they would have this PhD thesis distributed system. And I saw very consistently that they would put that in production and it would not work at all. And I would say, well, I know, I can tell you why, and there's reasons why, but yes, that PhD thesis will not work well there because of various reasons. Did you experience that as well?
Yeah, very much so. I think that is very true. I think PhD research is very maybe a bit controversial. It's a bit self-indulgent. It's like, okay, I can, me in my basement alone, I can create a very fancy system that solves a very fancy problem, but you are the only person in the world who thinks like that. The second you hand it over to someone, it's going to break. It's not going to work. We even encountered this over and over again. It's kind of a big life lesson for me. Looking at something that often they describe stuff as like, oh, that's just a science project. That's not real. Like that's not actually going to help. Um, I have many examples of this. I think that one that I mentioned that like the algorithm doesn't do a whole lot. It's all about like training the people. Like humans are messy. Um, there's another example where we were working with this giant pharma company, and this is actually during COVID, and they were manufacturing. I I don't know if it was some vaccine. I don't know if it was the COVID vaccine, but we were trying to help them with their logistics problem. This is like an optimization problem, and working with a PhD. So it's like PhD to PhD. We're all talking the same language, and they modeled it to this particular math problem. And they were like, we can't solve this problem. And so we took it and we actually solved it in like 5 minutes, like unambiguously solved it, provably solved. So they were blown away and like, oh, cool. And we thought, oh, great. We're going to have a huge customer here. We're going to move forward and build a product, integrate it. And then we asked the researchers, like, okay, let's go. Let's put this in production. And they were like, oh, no, I'm not part of production. I'm just a researcher here. And we're like, wait, what are you talking about? And they're like, don't you have some boss that runs a manufacturing system? We're like, I have never spoken to anybody. And we eventually got to like someone who kind of knew, like someone actually owned the business side of the vaccine manufacturing. And their general feedback was like, okay, here's the deal. To make a vaccine end to end, it's like billions and billions of dollars. And like, yes, the manufacturing part, it's true. And yeah, you can map it to a math problem, but it's like 0.1% of the entire end-to-end process of making a of making a vaccine. So I was like, yes, your thing did solve a thing, but it, in the grand scheme of it, it's a rounding error. And they're like, it's not important enough to bring your thing as a product to fix a rounding error. So, that was interesting. It's like, okay, that's where like business and academia clash, where you're like, look, I solved this great math problem. Let's do this. Give me lots of money. And then they're like, actually, it's worthless. Like, it's worth pennies to us. you know, Help me solve real problems. So that was a huge learning curve, and probably it's a very common learning curve for a lot of startups. But you need to start at the business. Like, don't talk to the researchers. I try to avoid people like me. Like, I don't want to talk to PhDs. PhDs are great, very smart. That's great. Don't really care. You don't know anything about the business. I need to go talk to the business person who actually sees the dollars and cents and sees the revenue and the profit. And I need to ask them, what is your top three pain? Like, what is killing you? That is the person who actually knows what matters. And they're probably not technical at all, and that's fine. These are not really technical things. But when you're trying to build a business and a startup, the technical stuff falls. That was maybe a hard lesson for me. It falls down in terms of priority. Like, it doesn't really matter what the technical thing is. The only thing that matters is like, is this a business problem for you? Um, no one cares about your degrees or what school you come from or how smart your algorithm is. Like, if it doesn't solve a major pain, then nobody's going to care. So that was a really hard lesson that we learned straight on. But I'll pause here. But that was a good
No,
one.
I love that story because it's so applicable in anything. The distance from business problem. If you are this far, if you're this far, if you're this far, you ideally want to be direct. And I keep
Yeah.
on seeing this in data of, oh, that's not my job. That's my manager's job. Who that manager then talks to this other project manager who then talks to the business. That doesn't work. You need to be like this. You need to have direct conversations, and until we start doing
Yeah.
that,
You got to get close to the business. Yeah. Otherwise, you'll just be in a vacuum doing a science project, and then you can pat yourself on the back. You built a really cool thing, but it's not going to go anywhere because no one cares outside of you. It's a tough lesson, but it's very real.
it is. Well, let's talk more about sync computing, and this is where we will transition to our whiteboard. So you're obviously at sync computing. Let's talk about what sync computing is.
Yeah. So at a really high level, I'll focus really on where sync is now and what we're doing. And so the problem that we're solving right now in kind of the cloud computing space is, I guess I'll try using the whiteboard. So
Yeah.
since it's here, so right now, if you want to submit something to the cloud, you need your code, right? And sorry, I have terrible handwriting, as you can see. You have your code, and then you need the resources, right? And so, meaning like, okay, you have your Python script, your JavaScript, or your Spark script, or your Databricks or Snowflake code and data, right? I'll add data here. And then you always have to specify the compute resources. Well, I need like this instance, or like an extra large warehouse, or like this much memory, this much storage, etc. And this all gets sent to the cloud, and then as an output, you get some sort of bill, you get some sort of runtime, you get some sort of latency, right? So you submit that to the cloud, and then okay, that cost me like $1,000 to run. Okay, and that took like 4 hours, and I have some various latency, right? And this is literally how the whole
To be
world.
clear, that latency is how long it took from the start of the job to the end of the job.
Yeah, latency and runtime, yeah, they're kind of coupled, but yeah, basically. But they're always outputs, right? They're always like the output of your code, data, and resources, like 1 and 2 there. It's always an output. And this is literally how the entire world works. This is how computing works fundamentally, right? In every category. What we're trying to do is kind of flip this vision, or what we're calling like declarative computing. Why can't you take this and flip it? So now, of course, you still need your code and data, but then instead of specifying resources, say I want to minimize costs, and I want it to run in 3 hours, right? And then I submit this to the cloud. And then something else in the middle figures out, oh, okay, I see where your coded data is. I see your objectives. You want to minimize costs. You want 3 hours. And then it actually runs it on the right. If something else in the middle figures out the right compute resources. And then the output is exactly what you asked for. It was, the minimum cost that you asked for. It ran in 3 hours, right? This central like box, this magical system is what we're trying to build at Sync. I'll pause here. Does that make sense? Like, how do you go from what are my computing goals, and then I don't really care about the resource. I don't care about hardware. Something else figure out the right hardware.
Yeah.
And
Yeah.
then hit
Basically,
move forward.
this is a shot in the dark right here. It's usually
Correct.
pretty arbitrary, or what I think most people do is they choose the biggest, baddest machine, or they choose it arbitrarily on some sort of cost, and they say, okay, $1 an hour sounds too much. I'll do 50 cents an hour. But yeah, I've done research, or I did an early project where I found out, oh, actually the smallest instances were actually the cheapest because we can distribute this out well. But that
Right.
declaration, I would prefer to do it this way and say, here's how I want to run this. Clouds are not behooved to do it this way. Clouds are behooved Clouds are not behooved to do it this way. Clouds want you to do it this way because you will do a
Yes.
suboptimal job.
Correct. They make a lot of money because people are just guessing. And so, I don't know what percentage, but it's a pretty hefty percentage of compute is really just because humans, maybe to tie it back to our earlier discussions, humans are messy, humans are not optimal, humans are not perfect. Many people just want to get up and running super fast. So they purposely pick big machines because they're just like, I just want to run. I don't care. I just go. Let's pick something big so it runs fast. Like whatever. I got to move on with my life. um, and the service providers are just making so much money on really nothing. Like it's just because we don't know what to pick. Like I don't know what the optimal compute resource is.
Yeah, that makes sense. And probably right now the engineers are saying, so what? And the probably the cost people, the CFO is saying, okay, I want this. So it's definitely
Yeah,
an
this is another
interesting job.
learning curve at Sync where the boots on the ground engineers are actually building this stuff. Many of them aren't really cost sensitive or cost aware. I don't blame them. They're just focused on building good code and good pipelines. Cost savings is rarely kind of a developer concern. And you're right, it is their bosses, their directors, VPs, CTOs who are like, what the heck is going on? Are we being careful here? Are we being efficient? Um, so in some sense, the bottom group there, this declarative computing concept, I think is in the advantage of the developers. Like, okay, we still don't want you to think about this stuff, right? Just pick a box that says minimize cost and run in what's your maximum runtime, and then let something else figure it out. So that's kind of what we're seeing. We hope that it's, very tempting and appetizing for the developers. And then it obviously makes business sense for the higher ups because we're going to make stuff more efficient.
Yeah.
Um,
Yeah, to tie it back to what we were saying is sometimes engineers will say, well, I can do this, but how do I figure out this? And it's
yeah.
because you're a business person that's over here. You need to
Yeah.
be asking them these questions. And we don't really ask these questions of, okay,
Correct.
well, how long does it need to run? Or what should we be optimizing for?
Correct.
Oftentimes
Yeah.
you'll get a snap response from the business of always cost. Well, if you just say, I want it to be as cheap as possible, but you don't ask that follow on question of time, yes, we can do it as cheap as possible on one box, but in the life of the universe, we won't get a result. So we need all of this data to kind of figure that out. And you do that by
Right.
talking to the business over here.
Correct. Yeah. Exactly. Yeah. So one other way of looking at what we're trying to do is we just want people to focus on the business objectives. And picking out memory and instances and all that stuff is kind of in the weeds, and who really cares? The only thing that really matters again is the business objective, right? Again, tying back to our earlier story, who cares about the technical stuff? Just hit my business goals. So we're kind of empowering more higher level folks to control things that typically in today's world the higher level business folks can't touch the compute. So like, I don't know. All I can do is yell at someone and I hope that they figure it out, but um, they can't actually do anything because it's the developer who actually controls it.
Well, speaking of the control, let's go on to the next whiteboard number 2 and
Hmm.
explain out, because I don't think most people know about how nodes are allocated and tasks are allocated in Spark. So if you go through that, I think that will help people understand this is how we then go through and cost optimize this.
Yeah, I'll try to explain it let me go to the next page. So at a high level, this is what we're doing. So like I mentioned, you have code. Oof, it's hard to write on this thing. Code, data, right? And then you submit this to the cloud. Sorry, this is like the cloud here, right? And the output is like, let's just look at cost, for example, right? So it's always like I'll make this a little prettier. It's always like one direction. You submit your code and data, and then it costs money, right? What we're doing is this. We are actually providing, this is sync. We are providing a feedback loop. And so in the old world, well, today's world, right, if this is time, and this is the cost of your job. In today's world, you provision resources. You're like, this is like 10 nodes, 10 workers, whatever you need, and then you run it, and then it just stays there, right? So this is today. Nothing improves, nothing changes. Your job costs $1,000 to run, and that just runs every day. What we're trying to do is like, okay, if you actually measure what's going on and feed it back and actually tune some of the settings here, you can get a different profile where instead it'll kind of look like this. We're like, oh, okay, this is basically what sync does. So what sync will do is it will actually learn your system. And we really focus on production runs. These are jobs that run on schedules every day versus like ad hoc research stuff. These are like actual like ETL pipelines. And so what we're doing is piggybacking on these recurring runs that run hourly, daily, et cetera. We're saying there's a wealth of information there. And you can even piggyback on that and start tuning parameters and actually start measuring for real the impact of various parameters. And when you start doing that and you feed it to kind of our secret sauce in this box here is really, this box here is our secret sauce, where it is this kind of our own home built machine learning algorithm that basically takes this information, feeds it in our model, and then we kind of figure out, oh, okay, we know what to change here. And so this thing is just a loop that goes over and over and over and over again. And that is basically what causes the cost to go down. So here I focus on cost, which is what most people want these days, but it can be any parameter. So it could be runtime. So we actually have some folks now who actually care more about runtime than cost because they have like strict SLAs, for example. Or in the ML or AI or LLM world, accuracy might be something. Anything that's quantifiable and has knobs you can tune, you can kind of map to this system. I'll pause here. Does that make sense? This kind of closed loop.
Yeah, yeah. All that integration with sync makes sense. But how do we tie that back to the actual Spark cluster, the physical makeup of that cluster?
Yeah. So for example, let's say, so in the Spark world, you have to have a cluster, right? And one of the big parameters is the number of workers. So this is like you're having one worker, you have 10 workers, you have 20 workers. And this all impacts basically how your tasks are distributed within Spark. And the hard part about any distributed system is you don't really know the mapping between the hardware resources and the runtime can be very unpredictable. So, for example, let's say this is number of workers. This is in Sparkland, right? And then let's say this is runtime. Oops. Runtime. Right. So most people might think, actually, a lot of cloud providers would just simply tell you that actually, actually, instead of runtime, sorry, let me do cost. A lot of cloud providers would just say, well, if you double the number of workers, your runtime doubles or your runtime gets cut in half. And so everything kind of cancels out and your costs are flat. Meaning if you have 10 workers, that's fine. It'll run 10 times faster versus one worker. Overall, everything cancels out and it's the same. The reality is that's not true at all. And you have something it's actually a fundamental computer science term called Amdahl's law, meaning actually eventually the number of workers stops scaling. So it is true. It might be flat for a little bit. I can change my color here, but whoops, that's a sticky note. It might be flat for a little bit, but eventually it'll turn into this. And eventually your costs are going to skyrocket. And, the big question is, when does this inflection point occur? Is this at 1 workers, 2 workers, 10 workers, 20, 100? Who really knows? And the problem is, if you're, let's say, in a hurry and you're just like, oh, let me just pick up 20 clusters, or actually in Databricks specifically right now, I think their default is like 8 workers. So let's say you're running Spark and you're like, all right, I'm going to pick 8 workers. And now you're sitting here. And for the exact same workload, you're paying a huge fee when in reality, you should be sitting here. You should be kind of at a lower cost point. And so this scaling trend of kind of the size of your cluster and the cost is very nonlinear. And so this is the fundamental problem that like people just don't know where they are. Maybe you're here, maybe you're actually pretty good, or maybe you're like way over here. And this is very code dependent and data dependent. In Sparkland, you could have a lot of skew. And when you have skew, that means one of your tasks can be choking your system. And actually, you might have 20 workers, but only one of them is actually chugging because you have this skew issue. And so,
Would you mind
um,
diagramming out that skew that might be helpful for
y-
people to understand this?
yeah, let me just,
Here, how about let's go to 3.
oh, yeah,
We can
let's go
we can
there.
always go back to 2 if needed.
So, kind of a typical drawing here is let's say this is processing. And then these are your tasks, right? And so, let's say you're running Spark, right? And you have a bunch of workers chugging on tasks. And ideally, you have like, let's say 3 tasks running and they're all in parallel and everything is great, right? This is what we would call a very happy world, happy path. But if you have data skew, what happens is one of these tasks dominates. And when this occurs, your cluster size doesn't matter anymore because, for simplicity's sake, let's just say each one of these is a worker, right? So this is a worker, this is a worker, this is a worker, this is a node. This is literally an instance on Amazon, for example. This is like one instance, a second, a third. At this time here, they're all done. Like there's nothing to do. Um, but this guy is still chugging. So a quarter of your cluster is working, whereas the 3 of them are just idle. And so now the question is, okay, well, did I really need 4 nodes here? Or maybe what I needed was, well, maybe I don't need that. And maybe because I have this crazy skew, like maybe I just need 2. So then I'm just like this. Again, these are very kind of cartoony examples, but if you have a cluster like this, and now it's like, all right, no, I only have 1 node that's kind of idle. That's fine. And this guy's still going. But you can imagine this cluster on the bottom is much cheaper than the cluster up here because actually I don't need, let's say this is 4 workers, like each one of these bars, let's say is a worker. And then it's like, oh, okay, I actually don't need 4. Like having 4 did nothing for me because this one guy is bottlenecking my system. I'm going to just go to 2. So now with 2, maybe that runtime is exactly the same, but I freed up 2 workers. That's like half the cost are gone. So this, for example, will give you like 50% cost savings. No impact to a lot of stuff like runtime, et cetera. But this is why distributed systems, distributed computing is so complicated because you can have issues like this. You could have choke points in your system. Another one that's not this one is like IO bottlenecks. Like a lot of times you're just reading files from S3 and you're just waiting for a long time. Or what if you have a trigger based thing or you're waiting for another job somewhere else to trigger and your code is literally paused and waiting and your entire cluster, you're spending hundreds and hundreds of dollars a minute and it's just because it's waiting. And so what is the correct size of the cluster, taking all of this complexity together, what cluster size makes sense? It's massively complicated. And it's not just a Spark thing. It could be a practical thing. Like again, it's a trigger based thing and you're waiting. Like, well, do you want a giant cluster that's just running and waiting for this trigger? Or maybe that should be a small cluster because it doesn't trigger very often. Once a month it triggers. Um, so there's a lot of complexity here in terms of like what is the right size cluster, and it's so bespoke, which is why in our model, if you go back a slide, but our machine learning model, we don't treat all Spark jobs the same. It's not like we have a set of 5 rules that like, okay, everyone just follow these 5 rules. We treat each one uniquely. We map out each one. So each one we understand, we capture a lot of statistics. We understand the performance of this job across different cluster settings, and we actually populate our model. And so if we're managing like 100 jobs for a company, we actually have 100 different models fine-tuned for each one, kind of optimizing what's happening there. Does that all make sense? Sorry, that was a big dump of
No, it
thoughts.
makes sense.
Here.
So kind of let's back up here. So here we have some sort of skew, and the skew could be due to a larger file, for example, or
Hmm.
a data skew. Um, and this, I think if I were talking to somebody and we were to see this, I would try to get them to solve it both ways. I would say, let's solve it operationally. Let's go down to 2 nodes, for example. But also,
Hmm.
I'd be looking at, why do you even have this skew in the first place? Did you
Correct.
not think through
Correct.
the problem, right?
Correct. Yeah.
And
Yeah. There are
if
two
we,
layers here. Yeah.
yeah,
Sorry. Go ahead.
and the other thing I would ask a two-part question is, why do you have this, and is it worth solving, or is it possible to solve? Because for
Correct.
problems like this, if you think about kind of what we were just talking about, of if it's a rounding error sort of cost difference once we optimize it, is it worth our engineering time to even go solve this skew right here? Because this may be let's just say a month of engineering effort. And if we just use, let's say, something like sync computing, and we optimize that down, we don't need to go after this problem. This problem is just a rounding error. So
Correct. Correct.
the part of what I want data engineers and people to think through is, there are several layers to a question. Don't just think about, oh, engineering problem, boom, I've got my keyboard in front of me and I'm going. Now we talk about the secondary and tertiary questions that we ask to figure out, is this a problem I need to solve?
Correct. Yeah, absolutely. You need to know, to be more tactical here, you can sort by like what are your most expensive jobs. And maybe you only do this kind of zoom in analysis on like your top 10 jobs. And then everything outside of that is like, like you said, they're all rounding errors. So like don't spend human time trying to fix rounding errors. Like that's kind of what we do. We can go in and automatically optimize thousands of jobs that you probably don't need to spend a human to come in and go and solve. Because like in aggregate it's a big cost, but like going one by one, job by job, is just a massive waste of time for a human. um, Other than maybe the top 10 jobs that, yeah, okay, that's probably worth it for an engineer to kind of go in and deep dive. um, but you're right, there are multiple layers here. There's the computing side, then there's like actually zooming in, like what's going on with the data, what's going on with the code. um, Sync's perspective is the infrastructure is a little bit easier to scale and create a product around. Once you start touching code and data, that gets a little scary because there's so much context and nuance. Automating that is really kind of is tricky.
Yeah. The other part I'll point out to people, let's say if they're, in case they're architecting something, a system like this, is when you're looking at keys and you're deciding on keys, that's usually where this problem manifests. Is keys are broken up into inherently files of some sort, or some sort of partition. And
Hmm.
so sometimes you will have, just because of that nature of humans, you'll get some smaller stuff here, just because, uh, for whatever circumstance. And you can have, uh, the Walmart problem is what I've come to call it, because I've hit it so many times at
Hmm.
companies. You'll have these other retailers. Those retailers will not be ever
Oh
be
yeah.
as big as Walmart. Your Walmart can be just this huge problem unto itself. And so you have to account for, do I break up Walmart? Do I do X, Y, Z with Walmart? For example, I've talked to them of, okay, do you know the store number? So maybe you break that down, instead of Walmart as a whole, you do store numbers, and so you start to
Yep.
break this up. So think about this. Ideally, you handle a situation like this at architecture time, at design time, not
Hmm.
later on. But if you do hit it later on, think through those questions.
Right. Right.
So you
Yeah,
were,
that this mixing of big jobs and little jobs actually surprisingly shows up in multiple kind of points in the stack. Like even if you have like this always on cluster and you have like thousands of little baby jobs, and then a Walmart comes in and the auto scaler, cranks up your cluster something huge, and then that Walmart job finishes, and then, well, you still stay at that like huge cluster size. It takes a little bit of time for the auto scaler to go down, and that's just a waste of money. But yeah, mixing small jobs, little jobs, this here at Skew, like this heterogeneous kind of computing is a hard problem to solve.
it is. So you started to give a list of the sorts of things that are contribute to a Spark cluster's cost or job cost. What are all those things that you've seen?
There are, lots of parameters within Spark, but the ones that we focus on are specifically cluster settings. So the number of workers, the instance size. So are you using a 2x large, a 4x large, an 8x large? Then there's like instance family. Should you use memory optimized, compute optimized? Then there's the driver setting. How big should the driver be? These are just direct cluster settings. And then as anyone who knows Spark, there's a long list of other kind of Spark settings like partition size, et cetera. We don't touch those today. We're just focusing on the cluster. We actually used to do it, but then we got some feedback from some folks saying like, actually, they prefer to set it for various business reasons. And they're like, please don't touch that. I'm like, oh, okay. All right. So we're trying to like figure out what is the universal set of parameters that we as a product can tune, then most people won't push back. And that's kind of why we're focusing more on the cluster side. And once you start to bleed into like code specific things, it gets a little tricky. Does that answer your question? Those are like the main knobs.
Well, there's also things like you touched on it before, but shuffle sorts and
Yeah.
so if people don't know that a shuffle sort when you're going over something like this, you're now IO bound, but more correctly, you're network bound when you're on a cloud, because this is all of these interconnects are networks. They're not local disks.
Correct.
So, and perhaps the other thing some people don't understand is your instance type also dictates your network as well. So are you, I assume that you're dealing with that as well as part of the cost optimization?
Yeah, as we kind of take it, we call it like a gray box approach where, so this thing you mentioned is a very real thing, but Spark jobs are very complex with many stages. So like this could be one of 100 stages within a job. At this point it's very network heavy. At this point it's very IO heavy. At this point it's very compute heavy. Like these jobs are a multitude of things that are going on. And so our approach is like, well, let's just kind of, in some sense, black box it. Let's just put all this together. It is all encompassed in runtime. The runtime of your job is a all-encompassing number that just kind of blurs all of this together. And the runtime also directly correlates to your cost. So our approach is to take, all right, there's a bunch of stuff going on in your Spark job. That's fine. Let's just put it all together into one number. And we have a model around it, but that's kind of our approach. Like we don't go so granular into each stage and like, oh, okay, let's optimize this network at this stage. Like first of all, it's hard to even access and change things at that granular level. And so what we do is we kind of step back and look at the whole pie end to end and see like what's going on here.
Okay. And as people are watching this, they may be thinking, "Hey, that's great. What are some? Would you share some ways or that people could do it this manually versus automatically?"
To do what we're doing, yeah. So that's what a lot of companies do today. So we do talk to a lot of companies that like they do try to tune clusters to reduce costs. Today, it's pretty much all a manual process. So you need, it's not very fancy. It's like in a Google sheet, and you tweak the parameters, and then you record it, and then you kind of see what cluster settings get you kind of the best runtime and cost. Unfortunately, what we're learning in the real world, like maybe again tying back to our earlier conversation, the real world is much messier. It's not so simple as just like, oh, I go from 5 to 6 workers or 7 workers, and then I find that 8 is the best, and I'm done. In reality, 2 of the biggest things that we see that impact these things, one is the data size is very variable or can be very variable. And then 2 is the spot market. So a lot of people use spot instances to kind of save money. And specifically in Databricks, but they have this thing called spot with fallback, meaning you're going to provision a cluster, and on Tuesday it happens to be all spot, which is great. You save like 50%. Great. On Wednesday, those machines aren't available, and you fall back to on-demand prices, and now your costs are double. And so you can see that's just the spot thing. And then it can be something hybrid in the middle where it's like 75% of the cost. So it can range from like 50% to 0% in terms of like the cost savings and the fluctuations. And then you have on top of that another variable that's moving is the data size. So data can be growing slowly over time. It can be random. It could be spiky. It could be periodic. Like during the day, you send out a lot of stuff, and then at night, you don't do much. And so these pipelines have so many moving parts that if you just are kind of simple and just say, okay, on Tuesday, I pick 8 workers, and on Wednesday, I pick 9 workers, and then I compare the two numbers. In reality, you're probably not comparing apples to apples. Like, okay, you're actually comparing an all spot cluster with 500 gigs of input data to an all demand cluster with 10 terabytes of, these are not the same thing. And so to say that like 10 workers was optimal is actually, you have garbage data. Like that is, you're not comparing the same thing. It makes this so hard is the amount of variation. And there's just a lot of statistics. So what Sync does is because we're plugged in and we're always grabbing this data every time it's running, we're actually capturing all of the statistics. We see the spot market and we see the data size variation. And only when you have all that information, then you can start making choices. Now you actually have data-driven statistics over like what mathematically is the best cluster for this job, given all this stuff that's kind of moving around. Does that make sense?
It does.
I don't know if that answered your question. Like doing it manually
yeah.
is hard.
Yeah. Yeah. Well, there's the other part of, okay, so if you're going to spend, let's say it becomes somebody's half-time job just to record all this data, somebody's half-time job, you have to pay that person. And my hunch is that you don't come out ahead at that point. It's
Yeah.
not inherently a human
Engineers are
thing.
very expensive. Yeah.
Yes.
And an individual job is not that expensive. So the ratio is not good. Yeah.
But I think your point about the spot market was probably the most interesting is if you can have an automated way, you can optimize your spot market and actually have even higher savings.
Yeah, there's actually a third kind of wrench in all this, which is Spark specific or probably any distributed system. Because these are distributed systems, right? You're working on like 10 nodes on Spot. At any time, randomly, an instance can get yanked, right? It can get killed. What does that do to your job? I mean, that's a pretty traumatic thing to happen to your Spark job. And sometimes it can be negligible. Sometimes we've seen it actually have pretty detrimental impact. Even just one worker out of 10 can double your runtime because the Spark job has to do a whole bunch of repair and recovery. It's like this thing just got yanked. And so your runtime can skyrocket. And then in the worst cases, sometimes it can even crash your job if it hits you at a really critical point and it just kills your job. So Spot is not risk-free. And so, but these are random events. So Spot kind of forces you have to do statistics. You can't do single point comparison Monday and Tuesday. Like Spot, you need lots of data because it's so noisy. So there's some times that we've seen where actually the cost reduction of Spot doesn't pay off because every other day you're losing workers and every other day your runtime is doubling. And so if you actually do the math, Spot is actually costs you way more. And actually the cheaper option is go to on demand where you never have a worker pulled. And now your runtime is much more stable. So like you're comparing averages now. Okay, so like the average on demand is actually much more economical than Spot.
Oh, that's interesting. You brought up something that I just want to diagram out, and that's your DAG creation, your directed acyclic graph. You kind of mentioned it offhand, but as you die at each one of these steps in the DAG, if you die here, or you die here, or wherever, whichever machine is holding that, you're going to have to go back through and recalculate. And depending on how you set that job up, you may have to go all the way back to the beginning to recalculate all the way through. And
correct.
That's a problem.
Yeah, that's a great illustration. Yeah, it's and it's random, right? It's not like a golden rule across all jobs. It is specific to each job, which again is why in the beginning, early days of Sync, we tried like heuristic rules that could apply globally. We just found it was horrendously inaccurate, and it would just fail so many times. So many edge cases where actually that rule doesn't make sense. Actually, that rule doesn't make sense. Or in this case, it didn't work. It's a very bespoke problem.
It reminds me of we're talking about AWS spot instances in this case, but there's also preemptible instances on GCP. And the reason I liked
Mhm.
preemptible instances on GCP is they had the mantra that it will fail early rather than fail later. And
Mhm.
that was the difference, or the issue I saw with AWS is any point in time this can be yanked, where Google was saying, yeah, if you're up for 10 minutes, you're probably good to go. And
That's
I think
nice.
that's all
That's a good
different.
policy.
I take it you aren't doing things with GCP then?
Not today. We're focused on AWS and Azure today. But I think that's just because most of the Databricks folks are there. But it's a growing market, obviously, and our vision is to expand to GCP
Okay.
eventually.
Yeah, yeah. Check that out. And I can't remember off the top of my head. I believe Azure has a similar thing, but Azure actually had an interesting one where you could pay based on CPU usage, and so uh, then you could get some best of both worlds. But
Mhm.
a lot of services on Azure aren't great, to put it nicely.
Yeah,
Sorry, Azure people. I'd love to see it work better, but it's pretty bad most of the time.
Azure is rough. You know what's hard are the quota limits on Azure. I don't know if you've run into this, but you're
Yep.
just running and running, and then all of a sudden everything stops. You're like, what? what? What's going on? And you're like, quota limits. Like, then you have to like email them. There's not even like a efficient way to like increase your quota. Like you have to email them. Then a day later they get back to you and like, well, your request was denied. You're like, what? Like, what am I supposed to do? um, if you're not an enterprise user, if you're not some big old company, like you're a small shop like us, they don't care so much about you. So it's hard to get your requests approved.
Yeah, probably that's the benefit to the smaller clouds is the usually I'll get decent support from Azure. The
Mhm.
unfortunate part is I have to use Azure support more than I should.
Yeah,
So that is the
that makes
give and the
sense.
take there.
Yeah, yeah,
Uh, uh,
yeah.
so uh, you talked about was there an original use case that was at MAT, or this was just a research?
You mean this what we're doing today at Sync?
The optimization that wasn't MIT wasn't doing this optimization themselves. It was more your research and then spitting out. Is that correct?
Oh, I see. Yeah, our original idea was again that like hardware thing. We're solving this particular optimization problem, and so where we landed was through a lot of kind of customer discovery and iterations and design partners to figure out. All right, here's an actual optimization problem that people actually need to be solved. Um, the learning curve for us was the optimization part, is critical, but what was hard is getting the information. So we built this closed loop because in the beginning, in the early days, we didn't have a closed loop product. And we just had to email people like, hey, can you send me your event log? Can you send me your stuff? Um, and depending on the busyness of that person, like sometimes they would send it, sometimes they would not, or they would send it, but then they wouldn't tell us that they changed something else. And we're like, shoot, now I'm not comparing apples to apples because they changed what we said, but they also threw in some other extra sauce on top. And we're like, well, now that screws up everything because the information is not clean, right? Um, and so that's why we had to evolve where we're at today. Where now it's just automated, and we're plugged in, and we are being fed immediately all of the information that we need, and it's very clean. And so that was probably a bigger step, kind of like the UPS story that I said. The optimization algorithm didn't take forever. The harder part was just the system to get the information in a repeatable and scalable and clean way. That was much harder.
Yes. Yeah. It turns out that the hard problem wasn't the hard problem you thought it was.
Yes. Yeah, the
Now,
math is actually the fun, easy problem, and the hard problem is honestly getting something that other people will adopt. There's something obviously I can adopt something kind of crazy and complex, but when you're dealing with customers and prospects and you're a startup, people are busy, and I don't blame them. They're busy. I got other stuff to do. I don't have time to like spend a week installing this crazy thing. Like if I click a few buttons and it's done, then I'm happy. But otherwise,
Uh,
I don't have time for you. Right.
I was on a call with one of the startups I work with, and we were going through they want to do a different pricing, and I told them, if you can't explain to me your pricing very clearly in 5 minutes, you don't have the right pricing model. And
Right.
it's because you, on your side, you live, eat, and breathe this stuff. This may be interesting as hell to you, this may be great, but on the other side of that person, you're on a time slice of, okay, if I can't understand this quickly, I'll just say, I'll go to somebody else, or I just won't do this. So
Right.
it's a really, really important thing for startups to understand. Your pricing should be pretty straightforward, idea pretty straightforward. Otherwise, people will not take the time to learn it or understand it.
Absolutely. Yeah. I think there's an old adage like don't fall in love with your stuff too much. Because no one else will have the passion that you have. So most people are just busy and they're just like, yeah, I'll give you 5 minutes. Like what is this?
Yes.
For you, it's your whole life. You know? But you got to remember, most people have other lives too, and they're busy and they don't really care that much. It's a tough pill to swallow, but it's very true.
It is. And you didn't say it specifically, but do you handle real-time workflows as well? Or is this only batch?
We focus today on batch. Um, yeah, we don't do like streaming today. So it is just kind of batch because of our system. We need a production run that's running regularly. We don't actually change anything while the job is running. We change it in between jobs, right? So the next time you spin up a cluster, that cluster will be different. We don't want to interfere in the middle of your job. Like let that thing run, and then we'll change it the next time the cluster is spun up.
Okay. And one thing you kind of touched on, but you didn't say specifically is, let's say somebody between runs changes something, let's just say a spill amount or RAM usage, something like that. You are accounting for that, or you say, okay, this is what I was going to try this time. I'm going to try it no matter what.
Yeah, that's a great question. This is something we're looking at, and we face this every day. Like something changed, like RAM, disk spill increased, runtime increased, shuffle time increased, data size increased. There's always a big fundamental question of, okay, was that normal? Like, okay, from here on out, like every other day, we're going to see this spike. Was that just some random developer doing something random once? And like that, or is it a random occurrence? I mean, randomly every week, we're going to get one of these. We don't know when. Um, and what we do today is we kind of like, identifying which mode we operate, like which one are you? You need to do this at scale, you have to capture statistics. So, okay, we got a spike once. Is that statistically significant or is that an outlier and we ignore it? But if we see the spike again and again and again, then that'll start informing our model. Like, okay, these signals are statistically significant. So this is a regularly recurring thing. So then our model will adjust. So um, that's kind of how we see it. It's like, okay, something changed, something huge happened, and like, how real is it? Is it permanent? And you have to that's why you need this recurring thing over and over and over again, because I need to know how regular is this? We're not talking to each developer of each workload. We're trying to automate this thing at scale. So all we have is the data. Does that make sense? Does that answer your
Yeah, it
question?
makes sense. Now, thinking about your roadmap, what's the most exciting thing you have on your roadmap?
Yeah, that's a great question. So as you can kind of tell by the backstory of Sync, today Sync is focused really on Databricks and Spark, but our background isn't really Spark specific. It's not like or the co-creators of Spark, right? We came at this from an optimization problem, and so our vision is to be a general compute optimization platform. There's nothing really special about Spark or Databricks to us. It's just a platform. We chose to start small and focus because we're a small team and we can't boil the ocean. And on our roadmap, we want to expand to much larger markets. For example, like containers, huge, potentially Kubernetes. There's a whole Snowflake world. In Amazon, there's like ECS, Fargate, EKS. And then there's just raw EC2 instances. So there's just kind of this massive open field of expansion that we can go to. And then there's even like GPUs. So that's a very interesting use case because obviously GPU costs are really crazy. And inference would be kind of our killer sweet spot because inference is that repeat thing over and over and over and over again, right? And so that is kind of our sweet spot of what we want to optimize. So our kind of next phase of the company, we're kind of doing the groundwork today, working with some design partners to figure out, okay, which one do we want to expand to? How do we want to architect it? How does that fit with the product? We're kind of doing that groundwork today. But that's, I think, the very exciting future. Like we've kind of learned a lot of lessons in the Databricks world, and next, like, okay, take those lessons and start scaling. Let's go to the next thing and keep on tackling.
Oh, that's a good plan. So now coming back to your background, I'm going to ask you a two-part question that's kind of both sides of the same coin, and that is, what advice would you give to someone to get out of academia?
Good question. So I'm trying to pull them out of academia. That's the question. That's a good question. We actually have some history of that. So I've actually done that in real life.
What'd you tell them? I assume you poached somebody out of an academic institution.
Yeah, I think my like real answer to this is like, well, first of all, like, are you happy? Like, do you like grad school? I think that's a dangerous question. I think most grad students would answer in the negative, especially when they're like 4 or 5 years deep. So let's take that off the table. But I think ultimately, what's the long-term goal of talking about PhD grad school specifically? I think, if you want to be a professor, obviously, like you got to do that. That makes a lot of sense. But if you just fundamentally like research, which is more like me, like I really enjoy research. I think it's a lot of fun. Then I think getting a PhD probably is worth it. Because then you could be a researcher at like a big company or something like that. But I think what kind of was my experience was that, research is fun, but it can be so divorced from reality. And, everyone wants to have an impact on society. Like I want to build something real that people use and enjoy and benefits something somewhere. And so I think if you're finding yourself kind of like where I was like, well, I'm doing this thing, but like, there's not a soul on this planet who's going to use this thing. And if you kind of feel like that and you're like, I want to do something more useful, then I think that might be the right inclination to kind of jump out and maybe join a startup or join a research group at a company. I think these days, unfortunately, a lot of the interesting research is being done in companies versus academia. So I would say, go be a research assistant at a big company. That might be a good alternative. But yeah, I would just say, if you're tired, if you just want to do like real stuff, you might want to leave academia.
All right, now let's turn the question around. Tell somebody to go into academia.
Good question. So aside from like the career thing, like if you want to be a professor, obviously you got to do that. I do think the benefits of academia. So I've had kind of an interesting perspective, right? So I come from academia, but I've been running the startup for a couple of years now, and I've been working with engineers and data scientists. Some have grad school experience, some don't. I think while I kind of maybe for fun kind of downplay grad school, there are some upsides, right? And I think what I've noticed is like people who go through the gauntlet of grad school, it's such an ambiguous time. Like you have 5 years to do whatever you want. There's no game plan. There's no project manager. There's no real boss. I mean, you have a professor, but more or less they're pretty loosey goosey. And so what I've noticed is that people who kind of go through that experience are really good at ambiguousness. Like They don't ask like, what's the goal? Like, what am I trying to do? Like, what's the next step? They're actually really good at listening here and there and kind of getting a good idea like what's going on. Like, all right, I see what's going on. I know what to do. I can figure it out. And I think that skill is really powerful, especially in a startup, because in a startup there are way more questions than answers, and there's no clear like, okay, do this task, do this task, do this task, you're done. It is so ambiguous, and you have a lot more ownership. Like, if you have an idea and you want to go do it, just go do it. Like, you don't need to go through 3 layers of approval, write up a PRD, or ask everyone. Just like, if you think this makes sense, like, we don't have enough bandwidth for oversight. So like, I got to trust your judgment. So like, if you think this is good and this will help, then like, just go do it. Um, and of course not, there are people who don't go to grad school who are really good at that too. But maybe the one trait I would say maybe a little bit stronger for people who do go through the grad school experience is that comfort of ambiguity, able to like move fast, cut through waiting and asking questions. And they're just like, this is obviously the best thing to do. I don't even need to ask anyone. This is what we have to do. Um, so that would be a really good skill I think you can get. And I think if you join a big company, especially if you're on the engineering side versus like data science or research, like, actually you might know better than me, Jesse, but like, it seems to be much more like order driven. Like, these are your Jira tickets. And there's a process. Follow this process. Do it. It's very, and it makes sense. You need that process. I'm not saying it's bad, but it's a different muscle than like, okay, I don't really know what to tell you what to do today. You just gotta like poke around and like, you write your own Jira ticket. You figure it out. I don't know. I don't have time. See you later. Bye. I'll talk to you next week. Let me know what you figure out. That's like what a startup's like. Whereas a big company is like, here's your giant backlog. Go. Right. I'm kind of curious your take, Jesse. Like, does that make sense, or is that like you disagree with kind of what I'm thinking?
No, I think you're right. I think that level of ambiguity is, if you are not if you're not comfortable with ambiguity, somebody's not going to be there looking over you saying this is what you need to do. As an
Yeah.
entrepreneur, and on the show I interview a lot of entrepreneurs, you're comfortable with two things. I would say ambiguity and risk. There's an inherent risk,
Okay.
and
Yeah.
then there's this. Okay, well, what do I do? Uh, Perhaps if anybody was watching this and they're thinking about starting a company, this is the thing I'll tell them is, you're going to get a ton of advice. And the difficult thing about entrepreneurship is choosing which advice to take.
Yes.
And because you'll get advice that's over here and over here. And for example, the advice you're probably getting right now on the direction. Should you go containers? Should you go this? Should you go that? It's going to be complete opposite ends, and it will be equally passionate from each side. And the difficulty lies on you, and it's your call, and it's going to be your head that says, I made this call, I have to live with it. And if you can't handle that, that's a difficult thing. There's a It's not just a management decision, it's a personal Jeff decision where Jeff is accountable specifically for that decision, and you can't
Yeah.
pawn that decision off.
Wow. That resonates very hard with me. For specifically for founders who want to create a company, that is some of the hardest decisions you're gonna have to make. Because any hard decision, half the team will be like, "This is stupid. What are you doing? This is the worst idea ever." And then the other half will be like, "Great, totally agree. Let's rock and roll." Right?
Yeah.
And you have to take punches. Like, man, you need really thick skin. I would love to maybe the last part of our conversation about like startup advice, like what it's like, but like, you need incredibly thick skin to found a company, because you're gonna get beaten up, punched, rejection city. This is not gonna work. It's gonna take longer than you think. Um, People are gonna doubt you. You're gonna be like, "Wow." But then some people will praise you. It's just this weird. You're like, Am I right? Like, I don't know. This person says I'm great. This person says this doesn't make any sense. And like, what do you do? And maybe what I've learned personally is I learned to trust my gut a lot more. That took some learning. I think in the beginning I was like, well, let me do a survey of the whole company and let me tally the votes and then I'll do this. So this way at least I can say I have majority rule and no one can be upset. I was very afraid of, in the beginning when especially when you're young, it's your first time, you don't want to like you want people to like you, be like, look, I made an informed decision. But I think that is most of the time that probably can work okay. But like for the really hard decisions, I think you gotta trust your gut and be like, ugh, that I don't believe in that. Because ultimately, especially as a founder, you have to be passionate about your company, right? And if you make a choice that's like, I really don't like it, but everyone says it's right, but I think it sucks. And then that passion is gonna eat you alive because it is just pain city making as a company. And if you're not passionate and you're not, fully believe in it, it might be the wrong choice, but at least you're passionate about it. And you'll figure out the twists and turns that you have to do. But to do that, you need that passion because there's no other reason to do a startup. There's no money, right? There's infinite risk. If you're not really passionate about it and just loving the journey, then you're not going to succeed. You won't survive. So sorry, I'm kind of lecturing here, but like my personal lesson: trust your gut. What do you believe in as the founder, the CEO? Right or wrong, do what you're passionate about and just go with it. Because in reality, also things can change. 6 months, here's a good example. We picked Databricks to start. This was way before the AI thing, before like LLMs, right? And at that time, we got advice that like actually at that thing, I think at that time Snowflake was bigger. We had to pick Snowflake or Databricks, and we picked Databricks. Most because it was very familiar to me. It was more open source. Culturally, it just made a lot more sense to me. Even though a lot of advice was like, go do Snowflake. It's much bigger. Like Snowflake's the future. Um, and then, better or not, that we picked that. That was my decision. That was the CEO decision. Like we're doing this full blown. And then, of course, the whole AI LLM thing came about. We had no idea what was going to happen, right? And now Databricks is like going nuts. And now Snowflake is a bit faltering in kind of the AI world. Um, and that you have no control of. Right? You have zero control over the macroeconomics and where the industry is going to go. And so, because there's so much that's unpredictable, you don't know what's going to happen. At least just pick the thing you like. You know what I mean? At least you can control that. Like, at least I like this thing. Like, I want to do this, and I don't know what the future is going to bring. It's so unpredictable. Um, Sorry, I'm lecturing, but this is a really
No,
big topic.
no, everything you said is beautiful. If I were sitting here, hopefully, very many startup people are thinking, watch this and take take Jeff's advice to heart. He's exactly right, and it will take you a while, and it will take you a lot of time to get somebody to tell you this. So just watch it now, think about it, reflect on it, because it's not. Jeff isn't trying to sell you something on this one. This is just straight good startup advice. The other way I do it is to say, 20 years from now, we're talking about this decision you made. Do you regret it or not? And for something macro like, Databricks versus Snowflake, you're probably not going to really care about that.
Yeah.
You just won't know. But an overall philosophy, an overall, did you take the money? Did you start the company? Those are things you're going to think about 20 years from now. And the reason I ask
Yeah.
about it in a 20-year time frame is you're going to be old enough and wise enough and maybe poor or maybe rich or whatever, and you're going to actually have a perspective of regret. And that's usually my metric of what you should have done or what you should be doing is, do you regret it or not? Will you regret it or not?
Hmm.
And so I was talking to somebody who was thinking about starting a business, and it was very clear that it would be a regret to not start a business. And when I talked to them about starting that business, everything changed about them. Their voice, the way they think about it, because you're exactly right. And until you've been there and done it, I I try to keep it PG on the show, but I described entrepreneurship as a punch in the stomach and then followed by a kick in the groin. And then sometimes it's like a repeat cycle, and you
Over and over again.
over and over again. And every
Yes.
time what happens is you will have to stand up and say, "Thank you, sir. May I have another?" And
Yes.
and it's kind of this crazy thing of the entire time it's happening, you're thinking, do I really want to do this? Do I really want to? It's this constant gut check. And if you aren't really convinced of it, and if you aren't really, don't really, haven't really decided, it is not, it's going to be really difficult to get through those times. Because what you
Yes.
see in these movies, what you see most of the time in media is this glorified Jeff went straight from 0 to 100 million ARR. Does not happen, or it
No.
happens very rarely, or nobody wants that there's a certain narrative they want. And so there, what's going to happen is you're going to get your funding and it's going to be down and it's going to go up and it's going to go down. And
Yep.
those down times are really tough. And you have to
Yep.
get back up every single time and say, "Thank you, sir. May I have another?" And that is so hard when you're down. It is so incredibly hard.
It it is. It is really hard. And so at least when you're down, you be like, well, at least I'm doing something I really believe in. Like, yeah, the XYZ didn't work out, but that's what I'm saying. Like, trust your gut because your gut is really what's your compass for what will make you kind of have to be selfish. This was a hard lesson for me. Maybe I tend to be kind of a people pleaser. I want to make sure everyone's happy. But I think for a founder and CEO, especially, you have to push a vision and an agenda. And that vision has to come from your passion. You can't fake passion. You can't lead a company and have an all hands and you're like, man, we're doing this thing. I don't really care about it. Like the whole company's gonna see it. Like, it's this weird leadership thing where if it's not in your bones that you really like what you're trying to do, everyone's gonna see it. I'm not saying people are gonna agree with you. Like a lot of times people are gonna disagree with you. Like, what's in your bones is wrong. I'm out of here. And that's fine. You have to take those lumps too. Um, but at least at the end of the day, I think you're right. 20 years later, do I regret X, Y, or Z? It's like, well, you know what? I followed what I truly believed. I followed like the vision. Because I think what's also hard is a company that has no vision. If you farm out the hard decisions and you're like, group survey, and every time it's just a group survey, and like, all right, this is wash my hands. I have no responsibility. It was the survey of the company. Um, I think that's a bad way to, at least my opinion, that's a dangerous way to go because then you're like, well, what the heck is this? Like, zigzag. You're not gonna have like a clear spear of vision. It's gonna be like random chaotic bouncing around. Um, so, anyways, this is a great topic. I think it's a hard lesson. I wish I could tell myself this when I was starting out because this is something you learn through like you said, the rinse cycle of just getting beaten up in every single way. It is a really painful journey. I think Elon Musk described it well. He's like founding companies like eating glass and looking down the the abyss of death or something like that. It's just like constant pain all the time. So, anyways, still go do it though. I encourage people to go make a company. it's
Yeah, you're
it's
still
good stuff.
smiling, still kicking, so it can't be too
Yeah,
bad.
I'm still here. Yeah, very true.
Well, Jeff, it's been a pleasure. Thank you so much for sharing so open and honestly and talking about this background in startups. I really appreciate you coming on the show. Thank you.
Yeah, thanks, Jesse. This was a lot of fun. Thanks for having me. Really appreciate it.